Hi guys, I'm Kauwe, and I'm a PhD student that's graduating this spring out of the University of Utah's Material Science Department. And I'm here, and I'm excited to present my research on materials exploration using machine learning. Now, I've titled my talk Accuracy, Uncertainty, and Inspectability. And that's because these are three key things that we've been able to bring to this area of research using a model architecture we developed called CrabNet. Now, before I talk about the research specifically, I want to shout out to the people in my lab who helped make it possible. The National Science Foundation has funded me for the last 4 years, so go them. And then Dr. Taylor Sparks has been my research advisor. He's been incredible in helping me with my research, and he's just a great influence as an academic researcher and as a friend. Dr. Jake Gracer was a colleague of mine. He was doing his PhD for about 3 years while I was doing mine. Graduated about 6 months ago. And I talked with him for hours discussing the pros and cons of machine learning. See, he did material synthesis and characterization, and I did stuff on a computer. And so we tried to bridge the gap there and came up with better tools because of it. And then Anthony and Ryan, they're both PhD students, and they helped me with the machine learning side of things. And they were really critical in the development of CrabNet and our thought processes behind it. Okay, so I want to talk about materials exploration. What I'm looking at here is a figure where the y-axis is the number of publications on a log scale, and the x-axis are years that have passed. So these lines represent the pairing of an energy term with the term materials. So battery materials, fuel cell materials, etc. And you'll notice that despite the fact that we've been trying to find better battery materials for the last 60, 70 years now, funding, or the number of publications has only increased. And that probably means funding has only increased and researchers interested in this area have increased. And that's because it's not a solved problem and it's very difficult to find new and better materials for these applications. Well, why is it so hard? Why do we have this problem here? That's tough to answer, but part of it is because it's just hard to find a dramatically new material when we do local optimization. That is, finding a system that we know works, like lithium batteries, and making it better. You're not going to find that, oh, turns out this other element is even better. So we can't find new materials or do materials exploration that way. But then what other way is there? Test things at random? So materials exploration is kind of a weird place. It's extremely risky. The payoff is probably zero, but if you do find something, it's awesome. Now, how we usually find things isn't by purposely searching in random space. Instead, we have happy little accidents, as Bob Ross would say. Serendipity just hits us, and we discover things on accident while trying to make something else. Vulcanized rubber, that's an example. A couple synthetic plastics. Teflon, some of your artificial sweeteners, super glue, like the list goes on. Now, all of this is the case because we don't know how to search in chemical space, and chemical space is huge. Now, if I have what I'm going to call an oracle, let's say it's my machine learning model that I trained for dozens of years with huge amounts of data, and it does essentially a perfect job of predicting materials properties. I could probably generate you a material that's really good, that does not look like the other materials people are working on for your given property. Let's say figure of merit for a thermoelectric. And so if I have this model, I can come up to Jake and I can say, hey, I want you to make this for me. And he's going to say, great, I need a facility, I need lab space, I need a press, I need a ball mill, I need a furnace, etc. He needs a lot of equipment because he's no longer in our lab. So, there's that upfront cost to get things started for each new researcher who wants to do materials exploration. And then he's going to have to purchase all the raw ingredients, which again is another little bit of cost. Once he's done that, he can sit down and he can say, okay, time to make something. That's his specialty. Well, I've asked him to bake this cake. I said, this is the best cake in the world, and instead of using wheat flour, it uses cornmeal. Go ahead and make it for me. And he's going to be like, you gave me the amounts of ingredients, but you told me nothing about the recipe. And so he's going to bake cakes, so to speak, over and over and over and over again, until eventually he gets one that he says, okay, this one's probably good. It hasn't totally collapsed, and I know how to bake cakes for the most part. I'm going to go ahead and measure this. But in the meantime, he spent maybe a couple weeks, maybe a month, trying to make anything at all that's useful. And that's really the synthesis task over here. Once he does have this material, once he's figured out his recipe and he's made a good version of it, it comes time to characterize it. You could think, how does the cake taste? I'm going to say, what's the materials property? Did it match our prediction? And if I have this perfect predictor, which of course is nonsense, he's going to ask, how close is it to that property prediction? Because that means I might need to make it better. I might need to change the recipe again. But regardless, he needs now equipment to characterize this. He luckily has the expertise to characterize this, and he's going to need a week because there's a lot of properties we're interested in. Now, that's if I have the perfect predictor, and that's just not going to happen because materials space is huge. It's massive. I'm going to quickly show you an example of just how absurdly big the problem is. Now we're looking at 4 component systems. That is 4 different elements at amounts as small as 3%, and there's 10 to the 12 combinations of it. So if we started at the size of the sun, this is our 10 to the 12 value here, and we scroll down, 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 we end up at 10 to the negative 3, so we need to keep going. We end up roughly here. So we're talking the difference between the diameter of the sun and the length of an ant. That is to say, if I lined up ants across the diameter of the sun, you're asking me to find which ants are the fastest of all of them and look the most different. It's an absurd task. But we're trying to solve it, in a manner of speaking. And to do that, we're trying to make as little bit of effort required and to maximize those results. In the way a lot of materials informaticists, that is material scientists who apply machine learning techniques, the way a lot of us think about this is to say, let's place these materials in space and measure an actual distance between materials to know if they're novel or not, and try to correlate their location in space or how space behaves to their materials property. This is an example. Let's say these are thermoelectric materials in some representational space. These red values represent candidates I'd want to find. Candidate number 2, that would represent local optimization, something close to what I'm already working on. Candidate number 1 represents something that's pretty far away compositionally, but hopefully has materials properties we want to take advantage of. Now, all of this depends on that representation. And we can represent things, and I'm going to show you how. So let's start with the element properties. We're going to use these. That is, look, we have hydrogen, helium, lithium, plus their columns. We're going to use these to create what's called a composition base. That means this is based on the chemical composition. Feature vector. That is a vector that puts us in this high-dimensional space. And so to do that, I'm showing you aluminum oxide. Al2O3, I'm going to normalize it to Al4O6. That just helps with some situations where your data might be just multiplied by a scalar. Al4O6, we want it to look like Al2O3. So here what I do is I take oxygen's properties, I take aluminum's properties, and I multiply the respective properties by the amount of each element. So 8 is multiplied by 0.6, 16 is multiplied by 0.6, and we do that across until we have 0.4 multiplied by 0.6. Similarly, we can take the average of aluminum's values, and that gets us this vector, which, if we project it into space, puts Al2O3 somewhere, and any other compound that's now projected in space has some distance from it. And I can start using that to do machine learning. Now, once I have this space, I'm ready to go. I can do a lot of stuff here. For example, this is me making the chemical composition. I've projected my elements into 2-dimensional space, 2 columns. And what you can see is NaCl lies right between Na and Cl. You can see Al2O3 lies a little bit closer to oxygen than it does aluminum. And we have calcium carbonate here. Now I've colored aluminum a different color than the other 2 because I don't have its label. And I want to do machine learning to find its label. What's the easiest approach? It's to ask, what's your nearest neighbor? In our case, NaCl. We have a distance metric. And to say, well, I'll just give you NaCl's value. Another approach might be to average the value of NaCl and CaCO2 based off of their distances. And if we do this, what we end up actually building is a linear regression. That's what I'm showing here. So that is, I'm trying to draw a line that given a material's property and given an element property can correlate them. In our case, I'm showing atomic radius, and these red circles represents data with labels, data where we know its atomic radius and its property. And I'd want to put something new there once I have my line. And so let's throw AL203 in there again. Given its atomic radius, that would be its vector. In this case, it's a size 1 vector. I'll generate its prediction. And that's machine learning in a nutshell. But not all data has this nice linear response. We might get something disgusting like this, a parabola. And in that case, we could use something more advanced, like a neural network, where the function that models this thing is not just a line, it's much more complicated. It's a bunch of lines that are stacked with nonlinearities inserted in them. And this gives us, well, if I have the X for aluminum oxide, I can again just get the prediction. And these techniques are all used. And essentially all it comes down to is given the material's representation, its vector, where it is in space, build a model that can predict where other materials might belong if you had their representations, their place in space. And so we've done that, and a lot of people have done that, and you get really good results. I'm showing you the prediction of heat capacity. These are real values from the NIST JANF tables. And on the left is a classic material science approach called the cation-anion contributions method. And there what they do is they take cations, anions, they associate property or heat capacities with those, and if you give it a composition that has those two things in it, or those three things, or whatever it is, you can assemble a prediction. But there's a caveat. You have to have that cation, anion, or those cations and anions, and it has to be within temperatures they've deemed appropriate. Now on the right-hand side is a machine learning approach where we break everything up into its elements, and we learn from those. And we have a huge range of temperatures, and we can just say, given any temperature, I'll just give you a prediction. And we can see on the left-hand side, we veer from that line pretty severely. And on the right-hand side, we don't hug quite as tight, but we're closer in general. And this shows machine learning excels at this task, and it's very complementary to other approaches. Okay, what we get here, and a few publications later, a few papers where we demonstrate different properties, different tasks, and we say this is good. But I sit here and I say, I'm still bothered by something. When I put in my elements, I have this fixed representation of them, just their properties, and it's averaged with the other elements. But in my mind, every element's representation should dynamically update based off of what other elements are there. And we need to change how these elements look in different systems. And that brought us to CrabNet. Now, CrabNet is a transformer in disguise. It's the transformer architecture from natural language processing used to perform attention in a material science space. Now, the transformer architecture, it's sort of revolutionized a lot of machine learning tasks, especially in 2020. People call it the year of the transformer. We got text translation from Google, text generation from OpenAI, question answering every Google search you do. Here we saw a transformer used in the application of an AI that beat professional StarCraft 2 players, a task a lot of reinforcement learning researchers thought wouldn't be possible. And on the right-hand side here, these little cats, that's image generation. So given a pixel, look at all the other pixels around you and predict the next value. Now, the similar theme with all of these tasks is you have items in a system, and you say, given this item in my system, what's the value of its item relative to all the other items that are present? So actively update your representation. So you come in with a vector, but you leave with a different vector based off of who's there. Well, if I have chemical composition, that could be my system, and each element in the chemical composition could be my vector, or could have a vector. And each element could look at all the other elements around it, and it could say, actually, that's not, I'm not oxygen bonded to carbon and hydrogen. I'm oxygen bonded to silicon, and that changes things. And now we have this cool dynamic way of changing element representations. And when we use attention from the transformer architecture, we just get really good machine learning. Because Google, Microsoft, Facebook, they've all poured millions of dollars into making this architecture as efficient, fast, and good at learning as possible. But we also get this active update of each element's representation via element-element interactions. And I'll show you these. It's called the attention map. And we can get at the end, since we don't collapse our elements into a single vector, we can get how each element contributes to our materials property. And then because I'm a nerd, there's a really fun thing where it's permutation invariant. You can switch which elements are where in your chemical composition. We know in reality that's not going to change what I just made. Well, this model, it's not going to change the prediction it just made. So that's nice. Well, we figured out a way to make material science problems look like natural language processing problems. And we put them through a transformer and we generated predictions. And at the end, we decided these look pretty good. Let's compare them to best practice approaches. Now, we generated a huge amount of benchmark data. Every single row here is benchmark data we found that other people have used online or that we gathered ourselves. And we compared that data to Roost, that's this left column, who's the current best practice when it comes to compositionally restricted materials predictions. And CrabNet is our approach. And then we have an approach we called Hot Crab, again our approach, but slightly different, which we compared to ElemNet. And then finally on the right-hand side is a benchmark everybody uses. The same type of learning we used in that heat capacity paper called Random Forest algorithm. And the results were, well, CrabNet did pretty darn good. I'm going to say about as good, and I don't want to say better because there's a lot of variation in the metrics you get with one of these predictions. But when we compared CrabNet to Roost, we saw this was performance on par with the best. Now, both of these methods come in with a chemical representation, that element's vector when it starts. They come in with a representation that's meaningful, and it's that same thing I projected down to 2 dimensions. We saw that elements clustered nicely together. Well, these other 2 approaches, Hot Crab and ElemNet, they come in with 0 chemical information. And it's their job to extract it from the data as it's learning to predict the property. Essentially correspond elements to each other if you can. And maybe at the end of the day, you can give us the chemical representations you've learned. And that's a work in progress. I'm not presenting that here. So we saw that CrabNet did good, but that really wasn't even what we set out to look for. I mean, we expected that it would do pretty nice if you updated these elements on the fly, but we also hoped to have inspectability. So we had that accuracy done and done. And what I'm showing you are those element interactions for the compound Al2O3 for the property bulk modulus. And this is what our model thinks oxygen and aluminum should look at after it's trained. So once this model can get a good prediction of bulk modulus given chemical composition, he'll tell us what he was looking at when he generated that prediction. So here I have rows for oxygen, which represents what oxygen's looking at. So oxygen's row is him looking at something. And I have columns, what's being looked at. Now, beautiful stuff can emerge from the application of transformers and the building of CrabNet, and that's storytelling. Now, this might not be a true story, but I can generate a prediction on a chemical compound, and I can go into my model and I can tell a story about what my model was thinking. And if it's a good story, if it's a true story, I might even be able to learn important stuff from it. So the story I'm going to tell here is, look at the oxygen column and look at aluminum's row. Aluminum looks at oxygen almost exclusively in 3 out of the 4 attention heads. And each attention head is a different perspective that we allow our model to have on the problem. So what that tells me, the story that's being told here is, when aluminum's in the presence of oxygen, its bulk modulus value is definitely different than when aluminum's in the presence of other things. And so aluminum has this light go off and says, I need to see that there's oxygen here so I can update my values, because oxygen's going to change things. On the other hand, oxygen's a little bit more reserved with its updates. It looks at aluminum in 2 of the 3 columns and says, I need to know aluminum's here. But in the other 2, it's fairly balanced in its prediction. It says, I need to keep the fact that I'm oxygen. And the story I might tell from this, maybe it's not true, is that oxygen makes oxides, which are typically all have high bulk modulus values. And aluminum, when it makes an oxide, needs to know that oxygen's there, but oxygen's not quite as concerned about the aluminum. Now, again, this is a story. It might not have truth, but we can keep telling stories, and we can maybe learn as we tell these stories. Here's a global perspective. Instead of looking at one compound's interaction, I asked, given silicon, so if silicon was a row, what columns does it pay attention to on average? So the average of all, we can look here, boron columns, goes to about 50% attention. So silicon pays about 50% of its attention to boron if it's in a system with it. And now I can look at these, the average of the attentions, and I can say, interesting, attention head A, it looks for n-type dopants. Attention head C, it looks for transition metals. And D and B are a little more ambiguous on what they're looking for. Maybe I didn't need that extra information and this is noise. Or maybe I don't know, silicon systems very well, and I should see what silicon does when it's in the presence of iron or chromium here on attention head D. And now to sort of finish telling these stories, on a model that we know is great, I can ask, once you've finished looking at everything around you, what's your average contribution to a property? And here I'm showing you bulk modulus. And we see that it matches researcher expectations, so maybe this is a good model. Tungsten, carbon, boron, nitrogen, these are high contributing things to bulk modulus, and these are elements we find in super hard materials. So there's a lot of inspectability we bring, and then kind of an afterthought, but something we're working on is uncertainty. So here on the left is the distribution of oxygen's bulk modulus contribution. Here on the right is us asking, but how certain is the model about this contribution? And the more data we have, our theory is the more certain our models can be. And if that allows us to justify gathering more data, and if it allows us to get better predictions, we'd be really excited about that. So here are contributions that we think CrabNet has brought to the table, and I'd love to answer questions.